I was pondering about which setups you could build that don't require intricate knowledge of functions or the knowledge of control structures that we have not talked about yet. Coincidentally, one of you guys asked us how we'd go about creating Chladni figures. So what are Chladni figures? Well, this guy here is called Ernst Chladni, German physicist and musician. And what he found out is that when you have a vibrating metal plate, and in times before speakers, you'd vibrate a metal plate with a violin bow. When you have this metal plate and put sand or dust on it, the sand and dust collects in certain areas to form intricate patterns, like these, or these here. And that is because a vibrating plate has nodes. That is, the plate vibrates in what's called a standing wave. So there are areas in the plate where the metal vibrates really strongly, and there are areas where the metal does not vibrate at all. And in these areas where the metal doesn't vibrate or vibrates very weakly, the dust and sand that you put on the plate collects and thus forms these patterns. And with a little bit of Googling, you can find these neat pages called Creating Digital Chladni Patterns. And when you scroll down all the way, you find this formula here, which is the mathematical model of these Chladni lines appearing on a rectangular metal plate. And what we can do, even with our very basic VEX knowledge, is take this formula, put it in Houdini, and create a digital Chladni plate. So let me just highlight this and copy it, and move over to Houdini. And in here, I want to drop down a grid, which will be our vibrating metal plate. Dive in, and let's decrease our grid size and increase the columns and rows. So we increase the resolution of our lines and of the resulting values. And immediately afterwards, we're going to drop down a point triangle. And for each point, we would like to calculate how strongly the plate vibrates. So let's just comment here and paste our formula. So this is the formula that we will be calculating. And this symbol here is a pi. So let's write this a bit differently. Pi times n times x times sine of pi times m times y plus b times the sine, and in the beginning this is a times the sine. Let's drag this out, it's going to be a long formula. So b times the sine of pi times m times x times the sine of pi times n times y. So this is a formula translated to how you would write this in VEX. And depending on the version of Houdini that you're using, pi is either globally defined, so you don't have to take care of defining pi yourself. Houdini just knows the value of pi. However, if you're using Houdini 16 or earlier, you have to define it manually. So what you will do is drop down float pi equals, and then either you look it up or you had someone force you to memorize it, so it's 3.14159265. That's pi, or at least its first few digits. So let's look at this formula again. The formula needs an x and a y value, and we will just use the grid coordinates for that. Set the grid to be oriented along the x and y axis like this. And we don't have to take care about just mapping those values. So let's do that. I am getting an error here because I'm trying to overwrite the definition of pi that Houdini 16.5 already has. So I will delete that. Just keep in mind that if you're working on Houdini 16 or lower, you will need to do that. Okay, so let's look at the formula again. We will plug in our x and our y coordinates at the points, and we will also need pi, which we already talked about, and then two scaling factors, a and b, for both parts of this equation that will get added, and then another two scaling factors, n and m, for the frequency of the oscillation in x and y axis. So let's define them using our trusty float sliders. Create the interface element. And we now have sliders for A, B, M, and N. And I already experimented with them a little bit, so let's set A to 1, B to minus 0.8, and M to, say, 4, and 2 for now. We can dial those in later. I just don't want them to be at 0, because I won't see any effect then. Next, we can immediately drop down this formula up here. Let's just decide what we want to do with the result. In our case, I suggest writing them to a point attribute. Let's call it amp for amplitude, and it should be a float. So f at amp, float amp, equals to, and then I will just take this ginormous formula, copy it, paste it here, and add a semicolon. Let's highlight this point here. Okay, what's going on here? Let's fix this. When we hover over this error message, we can see the tooltip saying that we referenced an undefined variable. Of course, we didn't expose our point positions x or y, so let's take care of that by going float x equals at p, that's our position, dot x, that's shorthand, for accessing our positions x component. Let's do the same thing for y. Float y equals at p dot y. And if we want to be super clean, we explicitly tell Houdini that p is a vector. Add a semicolon, and now everything executes fine. Let's save this, and let's display our amplitude value by dropping down a visualize node. Go to visualizers, and we'd like to visualize our attribute as a ramped color. Let's use the infrared preset, and our attribute should be amp. Let's wire this in here, highlight it, and we can see those patterns appearing here. Now let's try dialing in those values here, and we can see they start to look differently. However, they do not exactly look like those patterns we've seen on these metal plates. So let's check what's going on here by going into the geometry spreadsheet here, and we can see our values for amplitude. And we can see they range from about 1.7 to minus 1.7. But as we already mentioned, those Chladni lines appear in areas where the amplitude is around 0. So how can we modify our formula that instead of spitting out values of 0 where there's very little vibration, it spits out values closer to 1? Well, as we saw in the geometry spreadsheet, our amplitude goes from minus 1.7 to 1.7. And when you look at this formula here, you can see it is basically an addition of this side and of this side. So the addition is the last thing that's going on here. And when you look at these sides, again, you can see you multiply two sine waves together, and the sine of something by default will be in the range of minus 1 to 1. So both sides of this equation will be in the range of minus 1 to 1. So the lowest value when adding them simply would be minus 2, and the biggest value would be plus 2. However, what we're doing here is we scale those sides with the factors a and b that we dial in here. And thus, the extreme values of these formulas will be between minus 1.8 and plus 1.8. And we can calculate these extreme values. Let's call it float extreme. We can calculate this value by just adding the absolute values of a and b together. So it doesn't matter if this b is minus 0.8 or plus 0.8. What matters is just the absolute value of those two values. So let's do that. The absolute value of A plus the absolute value of B. So that's the extreme. And what I can do now is use this extreme to calculate a new value for our amp. So our attribute amp will be equal to the extreme value minus the amplitude that we already calculated. So the amplitude is how strong this thing vibrates at a given position. And by subtracting this vibration strength from the maximum vibration strength, we get exactly what we want. So let's do that. Let's see what comes out here. And of course, I think we need to take into account the absolute value here as well. That is because it does not matter if the plate is vibrating downward or upwards. We only care about the strength of the vibration, not the direction. And the plate can, when excited, move upwards or downwards. So by taking the absolute value of this value that our formula spit out, we cancel out if the plate is moving up or down, and we just care about the strength of the movement. That looks more like Chladni lines. Let's try dialing in those values. And we can see some patterns that look very similar to those Wikipedia photos we've seen. What we can do now are two things. On the one hand, we can drop down another point wrangle and, for example, use our current amplitude to displace the points, in this case in the z direction. So let's take our current point position and add to it a vector. And the vector should be 0 along x, 0 along y, and should have the value amp along the z-axis. Let's see if that works. Highlight this. We can see now, well, it's a bit strong, so maybe let's dial it back. Like this. We can see now we have those patterns extruded in space. However, if we want to simulate those sand grains falling on this plate, what we can do is just drop down a scatter node, wire in the point wrangle, and within the scatter node, check density attribute and pipe in our amplitude as a density attribute. Also, we'd like to uncheck the relax iterations, and let's increase the overall total count here. But as you see, we still have problems clearly seeing those Chladni lines. So what is happening here? Let's highlight our point wrangle and head into the geo spreadsheet. And we can see when we look at the amplitude, it is now varying between 0.25 and 1.62. So what we want in the end as a density attribute for our scatter sub is a value that is only positive where those Chladni lines should appear. So the simplest thing that we could do, even before we're thinking about fitting or ramping or remapping these values, is just subtract something from it, a value, so that we are only ending up with positive values in the regions of our plate where our amplitude is biggest. So our amplitude's maximum value is around 1.6, 1.7. So in our point wrangle after our last line, what we could try doing is just subtract some value from our amplitude. For example, in our case, let's say 1.4, and we can see now we are getting those sharper lines. Their sharpness will be even increased if we subtract even more and get closer to the overall maximum value. So the downside of manually subtracting a value just to be able to clearly distinguish those lines in the scatter sub is that as soon as I change my settings here, those lines will get blurry again because their maximum minimum value will differ. So let's use those maximum values that we already calculated up here to subtract them. And let's say we'd like to always subtract 90% of the maximum value. So instead of subtracting this constant value here, let's subtract our extreme value times 0.9. So we will end up with sharp creases no matter what values we're going to dial in here. And now for this to look a bit more realistic, as this plate is usually vibrating, what you could do is animate the global seed. So we'll just put in $FF, so the global seed will be equal to our current frame. And when we hit play now, we can see those vibrating, oscillating specks of dust on our Chladni plate. This is one of these examples that show how much can be done in Vex without actually knowing much programming. Because most of the stuff we've been doing in this tutorial is actually math and not programming. We didn't have any crazy loops, any weird arrays, and absolutely no control structures. All we did is just evaluate some formulas. And this exact case is one of the reasons why I prefer writing Vex over VOPs. It would be absolutely doable of plugging these formulas together in VOPs. However, you would end up with a nightmare of a node tree compared to these few lines of equations that you write down. Equations that you don't even have to come up with yourself, as we've seen here, because we found this equation on a really neat website that was dealing with the exact same problem that we were looking for. So I hope you had fun with this slight math detour, and we will be back to programming in the next tutorial. See you then.